So welcome everybody to another talk in our series talk at Tübingen. Today we have Yash Sharma here, who is a PhD student in Matthias Bethge's lab, and he focuses on robustness of machine learning models. He has been previously a researcher at Borealis AI and IBM Research, and does a lot of Kaggle competitions. So we're very much looking forward to your talk, Yash.
Thank you. Thanks for the introduction. So what I'll be discussing today is our recent work on trying to move the field of nonlinear disentanglement towards natural data and observing what are the challenges there and try to take steps in that direction. So this is joint work with David Klint and Lucas Schott, as well as with Yvonne, and Dylan Payton serves as a senior advisor with my two advisors, Wieland Brentel and Matthias Bethge. Okay, let's get started. So I just want to go and do an overview first. So I'd first like to go over what is disentanglement and briefly discuss why it can be seen as important. And then also give somewhat of a rundown on what the current field has done, where is the current state of work. I then want to analyze the current state of work and see, are the existing theoretical assumptions being made in current work realistic, as well as the data sets and metrics that we use, the existing benchmarks, are they also realistic? And this comes to our central question in our work. We want to see if disentanglement can be achieved theoretically, but not only theoretically, but also empirically, by assuming properties characteristic of natural dynamics and ensuring the assumptions that you make correspond to what is actually true with natural visual data. Okay, to get started, what is disentanglement? So assume that you have some state of the world. There are some discrete factors, and this is a very simple world where you say have shape, scale, orientation, X and Y position. And say you assume that given the state of the world, you can synthesize your observations. And this can be literally done in, for example, graphics engines and video games. And this could also be somewhat assumed just to provide you a formalism for representation learning in real visual data. So say we take this sort of standpoint that there is some state of the world, and that state of the world give rise to the observations that we see. Here on the side is a GIF of what would happen if we were to vary each of these factors independently. And this is the D-Sprites dataset. These are the D-Sprites factors, a common disentanglement dataset. Okay, so assuming this scenario, what is disentanglement? Well, what we want to do is, given these observations, we would want to get back to the state of the world. And in a sense, this formalizes the representation learning problem. The representation learning problem is attempting to take your unstructured data and be able to return what is the lower dimensional information within that said unstructured data. In this case, we have a ground truth for what that information should be. It's a state of the world. In reality, we don't have that. But if we did have that, then can we analyze how methods perform? That's essentially the gist here. So unfortunately, this problem has been shown to be impossible. So if one assumes that the state of the world is each of these factors are independent and this state is unknown to the model, and one assumes that the synthesis, the way you go from the state of the world to the observations, is a nonlinear process, it's been proven that this process of going from observations to the state of the world is impossible to guarantee. So identifiable is a term in nonlinear ICA to mean whether the model that you have can be guaranteed to yield the correct solution, where the correct solution is this particular state of the world. And it's been proven that this is impossible if you make no other assumptions or have no other inductive biases. So this was a general gist in our work that if you do have the inductive bias, but this inductive bias is assumed based on natural visual data and not based on anything that makes your proof work, then can you actually yield identifiability? Okay, so to formalize things a bit more, so here is the generative process I specified in the previous slide. You go from sources, which are the parameters of the world, and through some mixing process that you don't know, but you assume it exists, you get these images, and there the sources are entangled. Now, the approach that has been commonly used is to leverage not only autoencoders, but VAEs. And in VAEs, you autoencode, essentially, functionally. So You have an f of x, which goes from your images to a latent, and you have a z, which goes from your latents through a decoder to get your x. And the objective you optimize is to minimize the reconstruction error over said x with the observations that you saw, as well as enforce this KL term such that you try to enforce that whatever latent code you have is simple in a sense, such that the distribution here is at least close to, say, a unit Gaussian factorized prior. And so this objective, this approach has been taken by nearly all methods in disentanglement, especially the ones that consider quantitative disentanglement. And so it makes it fairly clear to summarize previous work. And this was done by challenging common assumptions by Francesco Locatello, who is our colleague here at MPIIS. And essentially, you can group the IID methods that have been proposed for this problem very simply and summarize them in such a way. So the first method, essentially for disentanglement, at least in the deep learning realm, was beta VAE. And there they did essentially the minimal thing, which was that prior, which I talked about, trying to keep the representation simple by keeping it close to, say, a unit Gaussian prior. They just increased the weight on that term. And they found that if they increase the weight on that term, empirically, you get more simpler representations, more efficient encoding. And if you minimize redundancy, then the latents need to be independent. So you end up with empirically seemingly disentangled representations. Anneal's VAE was a follow-up work on this, which suggested that rather than fixing the bottleneck capacity, rather than fixing the weight on that KL term, progressively increase it. So if you start off with a very small capacity, you initially bias your gradient trajectory to capture a simple solution. And then as you increase the capacity, it won't deviate too strongly as the trajectory has already been started. It will instead just try to succeed in generative modeling given this simple representation. And they showed promising empirical results for this. Factor VAE and beta TC-VAE, both of these works essentially observed that this bottlenecking of capacity was just an indirect way at trying to induce independence in your dimensions of your representations. And so they just directly optimized that. They penalized the dependencies into different implementations. And there's another work which also considers taking the aggregated posterior, so whatever is the optimal prior for the given posterior, and then try to match that to a factorized prior, which is a disentangled. So as you can see, the previous work in this field are all quite similar. They're all just taking a VAE and trying to add a regularization objective, which tries to make the representations essentially independent in different ways. So now, why did I say this is impossible? So the general gist of why it's impossible is that if you are allowed to do anything non-linearly to mix the sources and get the image observations, then you can easily induce artificial dependencies, and the structure, the statistics of the given sources might not be enforced in these images. And if you have no knowledge of this, then how can you get back to the sources if everything is entangled in the given images? So I'll give you a few examples that have been shown in previous work. So the original 1999 paper in Nonlinear ICA leveraged an argument, I believe, from the 50s, which was essentially that if you have a nonlinear process, then for any input variables, say random variables x1 and x2, you can always construct a y which is independent of x1. And thus, in the nonlinear case, if you're just looking for independent components of your data, your nonlinear mixing could have introduced artificial independence, and you could end up with a degenerate solution like x1 and y are your solution if you just try to enforce independence, which is what's done in ICA and what these disentanglement methods are essentially trying to regularize a VAE to do. So Locatello et al., they also had a proof, and they showed pretty concretely that there is an infinite family of mixing functions, so functions which mix the ground truth sources and give you your images, such that the Jacobian of it with respect to the sources is non-zero almost everywhere, meaning that if I change a component of the sources, if I just modify a single source, then all components in the output of the mixing function change, and thus it's fully entangled, the data. However, they prove that there's an infinite family where this is true, but the sources and the mixed sources have the same marginal distribution, meaning statistically, like from the perspective of the VAE, these solutions appear the same. However, one is fully entangled, but one is disentangled. And so here's another example, which is a bit more concrete towards VAEs. Imagine that this is the correct disentangled representation. And imagine you now scale it, you rotate the latents, and then you rescale it. So now these latents are clearly a rotation of the ground truth, but to a VAE, if you compute the elbow loss, the loss is the same. And the loss is the same because of the rotational symmetry assumption that Gaussians make. And so these are all examples of how when you're in the nonlinear case, and you're unsupervised and you don't know anything, it is impossible to guarantee that you will end up with the true solution. Okay, so, but now what about time? So that previous work was from 1999, and there's been a lot of time since then. So has there been any progress? Well, yes, and leveraging time, which is interesting because that is what humans see. Humans don't see IID examples, humans see videos. So they see temporal images. So it'd be interesting if time can enable you a solution to this problem. So let's say you're back to the state of the world that we had before. But let's say there are some dynamics. Like for example, in YouTube, there are some transitions. And we'll get back to this in a bit. So now you have pairs of observations and they're temporally consistent in some way. And you now want to do disentanglement. It's been proven that this is identifiable under certain assumptions. And what we wanted to do was look at those assumptions. But it's already a significant step to show that if you move past the IID case and you assume you have pairs of observations, often temporally, that you can possibly bypass this an impossibility theoretical result. And the first work on this, again from Havernian et al., was in 2016, called Time Contrastive Learning. I'll discuss what exactly the method is. It seems very heuristic, and then I'll try to provide some intuition towards why it works. Okay, so this method suggested rather than assuming you see an input, you observe a time series. Now say you divide that time series into T segments, say bins of equal size. You train an MOP to tell which segment, which of these T segments, a single data point comes from. So is there data point from this segment, is it from this segment, which one does it come from? And thus it's a classification problem where the number of segments are your number of classes. And thus you could do multinomial logistic regression on top of your feature extractor to learn this model and make your predictions. So this seems quite heuristic. So why does this work? Well, let's see how exactly it works. So what they theoretically showed is that if you assume data that follows the typical nonlinear ICA model, and thus you only assume that this could be any nonlinear mixing function, just assume that it's smooth and invertible, and your components are non-stationary. So for example, if you observe the whole time series, the variance is changing. Then if we apply TCL on the observed time series, and your MOP has a hidden layer where the dimensionalities are all equal, including the input dimensionality is equal to sources, which is obviously not true in practice given images are typically high dimensional, but this is just merely a theoretical result. They do show that you'll be able to identify the ground truth sources up to linear mixing and squaring. And this linear mixing, if the linear ICA conditions are satisfied, can be estimated by doing linear ICA on top of the MOP representation. So this is a significant step from the impossibility proof presented about 17 years before this paper. So I'll try to provide some intuition as to how it works, but I would suggest you take a look at this paper if things aren't a bit clear. So why does this work? Well, first of all, why does linear ICA work? Linear ICA assumes that this mixing function, the mixing function from your sources to your data, is linear. So if it's linear, this function can't introduce additional artificial dependencies. And thus the independent components of your data are the independent sources. And thus if you enforce independence, which is what ICA methods do, you should recover the sources because those are the independent components of the data. But as we discussed, if we assume this is a general nonlinear function, you can easily induce artificial dependencies and such. And thus the independent components, if you apply the same strategy, aren't necessarily the sources. However, if you make the additional assumption, which is made in this work, that the segments are independent, meaning this segment is independent of this segment, is independent of that segment, which they assume in their theory, then by making this independence assumption, you can have ensured that the independent components of the optimal representation of an algorithm, of a model, which has learned to disentangle the segments. If the segments are independent, then the independent components of that representation are the sources. And thus you can run ICA on top of that to recover the sources. So though this is a bit hand wavy and a bit high level, what I just generally want you to take away is that generally all this really means is if you have more constraints, you'll end up with a unique solution and you were just making additional assumptions. But something to keep in mind is if you buy this argument, I ask you to look at the proof to come up with your own intuition to this. If you buy this argument, can we actually assume this to be true? Can we actually assume that if we observe time series, that each segment is independent and statistically independent because we're learning statistical models? Okay, so the next year, Haverna et al. Produce another algorithm which makes different assumptions. So rather than assuming you have a full time series that you can split into segments, and these segments are independent, now assume that you have pairs, short time windows, and you simply assume that there is some conditional there, that there is some dependency that's consistent between the next observation and the current observation. And the approach here should be very familiar to those who are familiar with contrastive learning, where you take a short time window, you yield a negative example, you just randomly permute this example, and then you train an NN to discriminate Y, the positive pair, from Y star, the negative pair. So this is essentially the contrastive learning we know and love, just with one negative pair. And what they showed is if you do this algorithm, which again seems somewhat heuristic, you can prove identifiability up to arbitrary nonlinear element-wise transformations. And they suggested that you could get it even up to permutation, meaning that you can ensure that you capture the sources, but up to permutation, meaning any permuted version of sources is valid, but a linear transformation is not. So they suggested that you could get this with linear ICA, but they didn't prove it. But this is another identifiability result, which makes different assumptions by leveraging temporal information. Now, this was also shown in Disentanglement. It's similar in the vein that Locatello et al. 2018, the challenging common assumptions paper. Their theoretical result was essentially a generalization of the 1999 Haverna result, but in the realm of disentanglement and VAEs. This is very similar to the TCL and PCL that we discussed, which were only a few years before. So in this work, again, you assume you collect pairs of non-IID examples, but now there's a very fixed transition distribution you assume. You assume that there are some factors which are fixed, and you know the number of changing factors. So for example, let's say that this is the first latent, right? And you know that 2 factors change. So then in this example, only 2 of these factors have changed, and these factors have changed by uniform sampling from the other valid factor values. So though this seems somewhat unnatural, it is a specified transition distribution, and they showed that they bypassed their previous result in the 2018 paper by leveraging it, much in the same way as TCL and PCL. So the question is, those algorithms, at a high level, they're all using some temporal correspondence. They're moving beyond IID, which is nice, but do they really capture natural videos? So in order to endeavor into looking into this problem, what we want to do is we want to look at videos where we have objects, and YouTube VOS and YouTube VIS are very nice data sets which provide segmentation masks for a whole assortment of YouTube videos. And so here's one example, and here's another example. And so if you have the segmentation mask, one thing you can do quite easily is you can get X, Y, and scale. How? You can get X and Y by computing the center of mass of the segmentation mask. And you can get scale by measuring the area of the segmentation mask. And those are half of the factors considered in D-sprites. So given these are generative factors commonly accepted by the community, and now we have videos, can we now look at the transitions here and see what's going on for these factors? So what we find is quite striking. So on the bottom is the YouTube data set I discussed. And on the top is a data set that we derived from KITTI, which I will discuss a bit later. But these are quite different data sets. And we record X, Y, and area, and we just look at delta X, meaning XT minus 1, for all of our collected segmentation masks. So on YouTube, it's about 250,000 segmentation mask pairs, and on KITTI, there was about 90,000 segmentation mask pairs. And we histogrammed them, the delta X. And you can see these distributions look quite similar, and they're all very temporally sparse. And then we ensured that by taking a generalized normal distribution, where alpha equals 1 means a Laplace and alpha equals 2 means a Gaussian. So if you're have a alpha lower than 1, you're even sparser than a Laplace distribution. And we find that similarly across these transitions, despite the fact these are very different data sets, alpha equals 0.5, 0.6 is the optimal alpha to fit this distribution. These distributions are very similar, and they're all very sparse. So this is very interesting, that at least for X, Y, and area, transitions in natural videos, statistically, if we look at large-scale data sets, are temporally sparse. And that can be seen in these large-scale data sets that have been made available recently. So now, given we've seen this one property, there are many properties in natural videos, but this single property that the transitions, at least in the continuous variables, are temporally sparse. Can we now look at these previous algorithms and see whether they provide any guarantees with this particular type of transition? And we find that there are issues with all of them. So first, as a precursor, we don't consider TCL here, as TCL, as we collected pairs of metrics data, while TCL assumes that you have long time series where they have stationary segments. And I think it's an interesting question whether such a study can show that TCL also makes unrealistic assumptions, but I won't make any claims about that. However, PCL uses much of the same machinery as TCL. It was a paper published a single year after TCL. And it is applicable here, and it does assume pairs. So does it work for modeling these type of transitions? So what we find is if you actually look at the theory and you assume that it's a generalized normal distribution that is capturing the conditional, their assumptions are only met if alpha is greater than 1, which by definition means dense transitions. And this is interesting because their simulation was in a Laplacian case. But as they even mentioned, a Laplacian conditional is not covered under their theory, but a smooth approximation for Laplacian is covered. And they mention this, but they don't actually use it for running their simulation. So, but even if we keep them at their word that this would work similarly, a smooth approximation which fits their assumption was not provided for the class of sparse transitions. So, and alpha equals 1 is not what we found here. We found alpha is less than 1 here. So if we were to assume that this is the distribution that the transitions are under, PCL's theory with assumptions would be violated, which we feel is an issue. Now, if we consider the weakly supervised work, this is even more clear because it's a valuable work, but there was no intention to make this like mirror YouTube videos, for example. So first of all, the theory assumes that the number of factors changed is known and is fixed. So assuming that you know that 3 factors are changing in YouTube videos is very unreasonable. And also assuming that only 3 factors change all the time is also very reasonable. To be fair, the estimation procedure contributed can handle unknown or random k, but the setting was not proven. And that was a big pitch in the paper that we can bypass the impossibility shown in previous work. And even if we keep them at their word that unknown and random k could be possibly proven, there is another issue, which is the fact that the transitions are uniform and these distributions are clearly not uniform. So overall, previous work has made a significant step in leveraging temporal transitions to bypass this impossibility, but the assumptions they make are not derived from looking at natural data. So can we prove identifiability given this observation? Is there a fundamental reason why we can't, or was that just not considered in these previous works? So we can do that, and I'm gonna provide the high-level intuition as to why that actually is true. And if you can check out our work, or we could talk afterwards if you have any other questions. So again, we want to reflect this property. This inductive bias that objects in nature change sparsely that we're seeing on these large-scale data sets like YouTube and KITTI. So now, let's say we wanted to enforce a model prior. So the VAE model priors sort of denote what prior knowledge you assume about your data. Let's say we wanted to represent this inductive bias as a prior. How would you do that? Well, say you have X position and Y position here, and you have a 2-dimensional latent, for example. This distribution is a distribution of the next latent given the previous latent. So the previous latent here is this in blue X. So if you assume that objects in nature change sparsely, you'd want to use a sparse distribution to represent this quantity, that if we know ZT minus 1, that we only change sparsely such that we generate ZT. And what you can see, so this here is Laplacian. what you can see is that Laplacians are quite axis aligned, which would be critical for the proof. So now this figure is intended to demonstrate the intuition. So stars mean the ground truth, and without stars, you mean the model. So if you're referring to the ground truth, then what we have here is a bunch of example transitions that would be according to a Laplacian. And as you can see, it's axis aligned. Now here we have the example we had many slides ago, where if you were to rotate the latents, it will look the same to a typical VAE and all the disentanglement methods, at least the IID ones previously. Now, does this still hold true if we include this as a prior as well? Well, it doesn't, because in this case, axis alignment means that if Y changes, most likely X doesn't change. And this can be clearly seen here. If your Z1 star changes, that doesn't imply that Z0 star changes. So for example, we have movement in X, we have a small movement to Y or no movement at all, which honestly is also intuitive and real because I can move to the side. I don't need to always move diagonally. X and Y are controllable in reality, but possibly not statistically given dependencies in the data. But regardless, in this ground truth model, with axis alignment, you can move, when you move in X, you often don't move in the other lanes or in Y. However, if this is the true generative model, the Z0, Z1, then these are clearly entangled, that if you modify X, you reduce Y, or if you modify X, you increase Y. And these are the observations that such a generative model would yield, which are clearly different from this. And thus a model which is trained with this assumption, assuming that this should be the correct data, would not return a good loss for this particular data if it's actually enforcing this assumption. And that is the key overview of the proof, that if you make this assumption, this gives you axis alignment, and thus a rotation and any sort of entangling transform is going to be statistically different from whatever we use as the ground truth assumption. And as long as we enforce this, we can prove identifiability up to permutation, which means that whatever is the optimal solution for a model which enforces this assumption, and we ensure that enforces this assumption, will be the ground truth, as long as up to permutations, meaning if the ground truth is permuted, it still would be valid, which is a stronger result than previous work and also corresponds to actually what we see in natural data. Okay, so what we wanted to do is we wanted to minimize the number of confounders for testing our hypothesis. So we would do that by keeping ourselves in the VAE framework that everyone else has used and minimally adapt it to incorporate this prior so that we can empirically test, is it doing anything? So again, we need observations we need pairs in this scenario, similar to Locatello's work in PCL and TCL, or PCL specifically. And now we encode, and then this is the typical VAE assumption where you want the posterior to just be simple. So try to make it close to unit Gaussian factorized prior. And we want to decode, and we'll minimize reconstruction error. So all we do is we keep the forward pass all the same. We just add an additional term to the objective, which is rather than just enforcing this KL, the standard KL, which we do have some evidence might not be necessary, but let's just keep it like this so that we can minimize confounders. If we add this term where we also say that whatever is the posterior for the next latent, it should follow what is assumed by how we assume latents evolve. So X here is ZT minus 1. And if your posterior does not enforce this axis alignment, it doesn't enforce that oftentimes things should change only sparsely, then you would get high loss here. So this encourages whatever your posterior is to reflect what you assume about the transitions in the latents. Okay, so we talked about algorithms, so now let's talk about data. So the data, thankfully, in Locatello et al.'s very, very extensive evaluation, they released everything and for the community. And this is here at this URL, disentanglement lib. And what this means is the approaches, those IID approaches before, pre-trained models for those approaches, data sets commonly used in literature, as well as metrics commonly used in literature. And so here's like an example that corresponds to Sprites, and these are other examples of data sets, and we use all the data sets in disentanglement lib to validate our approach. Keep in mind there are a few issues here, and one issue is that all of these factors are discrete, and all metrics assume the factors are discrete, which isn't true. So if we were to consider YouTube data, right, and we were to consider what are the number of unique values of X, it would be effectively continuous. And I believe we've made a count of about 140,000 over the whole data set. So enforcing a discrete set of 140,000 is effectively continuous. However, the metrics that have been proposed for disentanglement do not capture continuity. And this is important because, in a sense, all of these factors are continuous in real data. So if you metrics can only work on discrete factors, that is quite an issue. The second thing is that all of these data sets assume IID sampling, which we know is theoretically impossible to get to work. So we would need to make a modification in order to run our algorithm as well as previous algorithms that bypass the theoretical issue. So we first show results on D-sprites, and I'll discuss how exactly we actually do that given the IID issue. So one thing that people do, and it's a qualitative measure, is you can vary each of your model latents, pass through the decoder, and just look at how it evolves. And so here's an example for SlowVAE. So you can see this seems to correspond to Y position, it seems to correspond to X position, this seems to correspond to scale. The other factors, shape and orientation, they seem somewhat entangled. And I'll go into why that is the case in a bit. So now a quantitative evaluation would be to compare your model latents to the ground truth latents given you know it on these toy data sets. So you would measure the difference between encoded latents and whatever is the ground truth that rendered these observations your model is seeing. And there's many metrics. We can talk more in detail about what they actually mean if you're interested, but I don't think we have the time. And all these metrics have their own pros and cons. So we just wanted to evaluate over all of them and just play the game that previous methods have played. So beta VAE was our comparison method. The Locatello et al. Previous paper had shown that all these methods perform similarly. So according to that paper, it is not a big issue to consider this as the IID model. We compared to the weekly supervised paper, the 2021, on their uniform transitions. We trained our model on their transitions, and we trained our model assuming that the transitions are Laplacian. And so what was done there is that within the D-sprites data set, for generating your pair, you first sample the first latent uniformly, and for the second latent, you center a Laplacian and then sample whatever is the next latent provided in the data set that corresponds to whatever the Laplacian was. So you're limited by the fixed data set that's been provided, but you can still enforce Laplacian transitions in a somewhat discrete way. And as we can see, if we match our assumptions, we perform better. And if we even go with uniform transitions, which actually violates the theory, we perform comparably to the model that has been fit to the uniform transitions. So one thing we wanted to do is wanted to go a step further and not just look at latent traversals and the quantitative metrics, because it's a bit of a flawed evaluation. We wanted to see if we could learn something more. And one, as mentioned, Locatello et al., the 2018 paper showed that these IID models all perform similarly. But we somewhat challenged that statement by showing that if you visualize the latents and plot them, that's in a sense not the case. But it's somewhat true. So what we did here is we took MCC, which is a metric from nonlinear ICA, again from Haverne et al., and we computed it across all of these data sets. I'll briefly discuss what MCC is. What MCC is that, for example, you have the latents here. Let's say you have 10 latent dimensions. You have the ground truth factors for the columns. You have 5 ground truth factors. And you first, using some similarity metric, you first match latents to factors. And then after you've matched latents to factors, now you compute the diagonal. And then for the diagonal, you take the mean over here and you use some correlation coefficient. So what has been previously used has been linear correlation and Spearman correlation. We use Spearman correlation to account for nonlinear tendencies. However, Spearman correlation assumes monotonic structure, which is problematic. And I'll talk about why it's problematic in a moment. So we compute the correlation matrix to get the MCC score. So the MCC scores are all similar, but for DIP-VAE, which according to disentanglement scores seems to be similar to these models, it's significantly worse, which was not observed or not clear from the given disentanglement matrix. And then how do we select these models? Well, Locatello et al. Thankfully released all the pre-trained models. So for the model that we evaluate, we can select the best one according to the disentanglement metrics. So we take the mean over the disentanglement metrics, we get the best DIP-VAE1, for example, and then we can compute MCC and visualize the latents. Okay, so now if we were to look at visualizing the latents, on this side is the model latents, or the y-axis. On the x-axis is the ground truth factors. And the color coding is for shape. So for example, given there are only 3 shapes, you can look at how the orientation varies for respect to the blue shape, which could be heart, or the yellow shape, which could be a circle. So if how the model represents a circle rotating versus how the model represents a heart rotating. So what we can see here is that if you look at shape, and then you look at the model latents, this is entirely entangled because there is no distinction between the model latents. The model latents could be anything. If, for example, you have a heart shape, or if you, for example, have a circle shape. But if you look at SlowVAE, it is separated. So if you have a heart shape, the model latents are around this value. If you have a circle shape, it's around this value. For the third shape, it's around this value. But the score is low. So why is the score low? Because Spearman correlation assumes a monotonic relationship. So this somewhat indicates that, for example, for continuous factors like X and Y position and scale, these metrics are great. And they account for nonlinear dependencies, which is great. But for a method, for a factor, a categorical factor like shape, where there isn't any order, it's very inappropriate. So some work needs to be done on the metric side in order to account for that and give a fair evaluation for, say, categorical factors. But if we were to look at, say, theta rotation, that's similar. There's no monotonic, like theta rotation isn't monotonic because you can go from 353 degrees to 360 degrees, and that actually goes completely around the circle. In this scenario, we can see all the scores are low, but we claim that this is not an issue with evaluation metrics. This is just an evaluation with orientation in general. It's just hard to pick up, and we will discuss why later on. Okay, so that's D-sprites. But can we use the natural transitions that we use for analysis for something here? Because these data sets are obviously limited. All we were able to do is use what was used in previous work or assume some Laplacian conditional. But what if we wanted to actually have natural dynamics and not just analyze natural dynamics, see a Laplacian fits decently well, and then just fix that Laplacian distribution? Well, so we introduced 2 data sets for that purpose, both which have their own uses. So for natural sprites, we use YouTube for this. So in this case, we essentially tried to use the sprite world graphics engine to be able to render our own examples and thus not be limited by the dsprites dataset. We attempted to keep it as close as possible to dsprites, at least in the factors. And then we have these simple shapes that come out. However, what is the difference here? The difference here is that we measured X, Y, and scale on YouTube, which means that when we generate the transition for X, Y, and scale, we can sample a transition from YouTube and use the delta X, the delta Y, and the delta scale for the actual delta X, delta Y, and delta scale within the actual ground truth factors, and then render the observation that way. So rather than assuming some Laplacian conditional, we just literally take the values from the large scale data set that we've recorded. So you might say, though, that, well, how do you evaluate it given that's continuous? So we can only use MCC in the continuous case, but one other thing that we did is that we discretized the YouTube transitions. So if we want to go to the granularity of D-sprites, that's about 32 positions. So you can take a histogram over the delta X, and then you can bin it into 32 bins, and now you have 32 discrete factors. So in order to run the normal, typical disentanglement evaluation, just for comparability, we also discretized the granularity of D-sprites. The second data set we used, which I guess is more natural but comes with its own cons, is to directly use the pedestrian mass that we extracted from KITTI. So as you guys probably know, the KITTI data set was recorded autonomous driving video, which means that there is some like 3D aspect here that is somewhat confounding things. And it's just a difficult data set in terms of continuous shape as well as continuous position and such. The nice thing though, is that we can use the masks. And if we use the masks, then the complexity issues that VAEs have in terms of handling real textures, that confounder can be removed. And we can just see if we have natural dynamics with continuous shape and such, but still on the level of visual complexity that VAEs currently can handle well, what do we see? So the main problem though with this data set is the fact that it's real. And so if it's real, then we don't know what the ground truth factors are. The big reason to do this is that you can have knowledge of the ground truth factors if you simply augment, for example, the D-sprites render. But if we just take KITTI pedestrian mass, we have no idea what the ground truth factors are, which is a core problem in disentanglement. If we want this to be a formalism for evaluating representation learning, then we really shouldn't make unreasonable assumptions that will absolutely never be true on the data sets that we care about. If we care about vision, then YouTube care data sets like this. So we take a step towards trying to run evaluation there, but this essentially just highlights this missing component in disentangled research, one of the many, which is one can say that VAEs don't scale beyond D-spreads complexity, but even if they were able to, how would you evaluate? And that's still a question. What we did here is that we assumed that, okay, object properties such as center of mass and such as scale are things we should expect to be decodable from a good representation. So we justified evaluating just with respect to X, Y, and scale. And in that sense, we can run evaluation, a quantitative evaluation, but of course, this question isn't answered. So it's definitely something that's good to think about. How can we evaluate representation learning in a formal way on real data sets given the ground truth is unknown? Okay, so let's look at some results. So you can look at latent traversals and you see something interesting here. So this appears to be X. This appears to be something like X as well, but now with some 3D aspect to it. This appears to be Y in some sense. This appears to be scale. And the other latents have some interesting things going on. So like this looks to be a rotating pedestrian, which is interesting. And this looks to be a walking pedestrian. So it's interesting to see what these models end up encoding within their 10 latents, especially when the ground truth factors are unknown. And it's something that's capable because it's the same visual complexity as previous data sets, but it's obviously much more interesting than, say, a D-sprites data set. So now we can also do quantitative evaluation, but again, only MCC has been proposed in the continuous framework. Disentanglement lib, none of those metrics can work on discrete factors without modification. And we can see here that we outperform beta VAE fairly strongly. And then if we were to look at natural sprites and KITTI masks, and we were only to look at the X, Y, and area, you can see outperformance, but significantly better outperformance than KITTI masks. And I would like to note that the reason why the MCC scores are so much lower for such a simpler data set is because the shape and the orientation factor are still evaluated here. And those are factors which are always hard to capture for all of these VAE-based methods. And we'll discuss exactly why later. So in recent work, what we wanted to look at is, so all we did was compare against the IID-based methods here. And a big reason was that PCL was only proposed in toy scenarios where you have like ground truth simulation data, which is 20-dimensional inputs, and they're just vectors. And the code for the weakly supervised models had not been released. But the code for the weakly supervised model was released about 3 or 4 weeks ago. And so we could translate their model into PyTorch and run it as evaluation, and then be able to run that on our new data sets. And for PCL, we can just leverage the implementation details that we were using and just use the PCL objective. And as we can see here, we somewhat confirm previous results in these works in that they perform significantly better than the IID models, so beta VAE. However, we can see that if we go over all the data sets that we consider, the one model which is somewhat robust is SlowVAE. So modularity was already shown in the Locatello 2018 paper to be anti-correlated from all the other metrics. But that is a case where SlowVAE performs statistically significant the worst on. However, if we consider all of the other metrics, then in the uniform transition case, PCL has a Laplacian objective, and thus it performs very poorly. SlowVAE also has a Laplacian objective, but it seems much more robust to the mismatch. If we go into Laplace dataset, now PCL performs pretty decently, but SlowVAE still wins with statistical significance on a number of factors. But now the Locatello model, which was proposed for uniform transitions, performs poorly. And then if we look at natural sprites, it's challenging, likely due to the shape and orientation issues that we'll discuss. But then on KITTI, PCL performs poorly, but SlowVAE wins with statistical significance as long as you have like a somewhat of a transition. So not just the next frame, but 5 frames later. So overall, over the whole scenario, like overall the data sets, these previous works do outperform IID models, even PCL when trivially scaled up. But the issue is that these approaches appear to be less robust and also worse performing on the natural data sets. So if we would do the qualitative comparison again, I will look at these 2 columns because the rest of them are the same. We can see again some issues. So for example, we have a high correlation here, but this was essentially just random because shape again has no order, and this was yielded because the model, this particular model had shape as an order. But if you look at any other of the many seeds we train with PCL, they don't. So again, it shows a stochasticity here, but if you actually enforce the order, now you have a high score when shape has no order. But then if you, in addition, you can see that, like if you consider disentanglement based on a single latent is encoding a factor, PCL performs poorly. And you can actually see that if you look at the MIG and MCC scores. So if you look at MIG, SlowVAE is 10% better than PCL and statistically significantly better than the previous results. But on MCC, the scores appear to be the same. And you can see that by looking at how the diagonal appears to be great, except for orientation. But there's quite a lot of latents which also equally encoded. And what MIG is taking the best latent and taking the second base latent and computing the difference, which is intended on saying that only a single latent should encode the ground truth factor, and thus PCL performs significantly worse than with MCC. So we can see that these metrics all evaluate somewhat different things, and we do not have a universal metric, even if we also consider nonlinear ICA as a standard metric, MCC. And then if we were to look at the results, we can see that in a sense, PCL has somewhat separated the transitions for different shapes, which is interesting on one hand, but it also indicates that these expositions are the same regardless of which shape it is. So there's an argument that they should be grouped together. There's an argument they should be separated, but we can definitely do see a difference if we look at these plot visualizations. Okay, so I'll quickly go over this. You might say that we evaluated all these realistic data sets, but we didn't evaluate our theory because there's always going to be some mismatch between theory and these more realistic data sets. So what we did is we evaluated in the state of PCL's theory. So PCL simulation was completely adapted to their theory with a lot of different heuristic choices, like the use of leaky reloos as for mixing and to ensure that the encoder has the exact same capacity as the mixing network, and to use 20-dimensional latents, and to do PCA, and to do whitening. And then to quantify the amount of mixing based upon just increasing number of layers, and to heuristically try to ensure that the mixing is invertible by just somewhat controlling the condition number with selected hyperparameters which aren't necessarily validated. So regardless, despite all those differences, we just wanted to see if we go into their setting, if we compare to in PCL setting. And what we found is that in the setting where the inputs are 20-dimensional as well as the latents are 20-dimensional, there is no bottleneck for the VAE, and we end up with posterior collapse, indicating pros and cons of the estimation method. But if we were to use a flow-based model here, and thus optimize the explicit likelihood exactly, then it works extremely well if we use a normalizing flow model. And then you might say the architectures are different, and so we also ran PCL with the normalizing flow model, and it still was worse. So this somewhat highlights pros and cons between estimation methods. If you use a VAE, it's very scalable to real data sets because you aren't constrained to have the latent dimensionality be equal to the input dimensionality. But once you go to a data set where that's actually true, and everything is lower dimensional, it's very prone to posterior collapse, where a flow-based model is not prone to it. So it's an interesting thing to think about separating your model assumptions from the actual estimation method you use, because you can easily use the same assumptions with a flow-based model. And I urge you to check out our paper to see these results. So what now? So we observed that objects in nature change sparsely. And we showed that with a sparse transition prior, just making an assumption based on what we actually see in natural video and not making assumptions just generally, we can show that we can also prove identifiability there when previous theory has mismatch when we actually look at the statistics of natural transitions. Empirically and theoretically, we provide a validation, and on naturalistic dynamics, which we contribute to literature, we improve performance. So the biggest question is, of course, how to scale to real complex scene. This was just trying to validate our theoretical proof by minimizing the number of confounders by using the same setting as previously. But of course, such constrained VAE models will likely struggle on real complex scenes. There's an unclear submission which suggests that if you scale up the VAE, you'll be able to deal with visual complexity better, but that visual complexity pales in comparison to, say, YouTube or KITTI. So, of course, this is an interesting question, but this is also an obvious question. So what are questions that we learned from our work that weren't really exposed and weren't really obvious? Well, back to the categorical and orientation factors. So how do we treat this? How do we fairly evaluate this? And how do we also enforce in the model this distinction that some factors are continuous and monotonic, like X, Y scale, and some factors are categorical? And how do we treat this in a general way, which isn't overfit to like the particular factors we're looking at? And also for orientation, how do we treat variables with periodic boundary conditions? So here's a scatter plot comparing the second latent to the fifth latent. And we can see here that there's a very periodic structure to these latents. And what we found is that the reason why the scores are low for every single model on capturing orientation is because they all struggle to capture orientation within a single latent. They require 2 latents in order to encode it. And that's obviously not allowed under these particular metrics. A single latent needs to encode a single factor. And so there's a couple questions here. Can you do a modeling change that will allow you to encode angular factors into a single latent? Or can we generalize disentanglement theory such that we aren't forced to have a single latent dimension capture a single ground truth factor? So there's recent work from DeepMind called Geomancer, and in that scenario, in a very choice scenario where they assume they have quite a lot of information, they do show an instance of disentanglement with respect to subspaces, as opposed to disentanglement with respect to individual latent dimensions. And it'll be an interesting place to look for additional work, but I would just note that that work is definitely in its infancy, and it's definitely require significant work in order to be able to enforce disentanglement with respect to subspaces anywhere close to the complexity of even the disentanglement datasets. Okay, so I'd like to thank the other authors who worked on this paper and made this a reality. And thanks for listening. If you're interested in the algorithms or the data sets or just our experimental evaluation, the code is here. If you're interested in the paper, this is the archive. And if you found the work interesting, feel free to follow us for additional work in this space. Thanks again.